So my slide is visible to you all, spectral reflectance curves. My voice is audible? Anyone?
Yes.
Yeah, great. So we are good to go. We'll proceed again. Now we will see some spectral reflectance curves, which will be useful for us to further understand how we can use remote sensing for accepting the features on the surface of the Earth. Now I will show you three classes of land use land cover, mostly vegetation, air, soil, and water, how the spectral reflectance curves of this Earth feature looks like. Okay, we will see now. Before that, I already told you that spectral reflectance is the ratio of reflected energy to the ratio of incident energy, ER of lambda divided by EI of lambda. That is energy of wavelength lambda reflected from the object and energy of wavelength lambda incident on the object into 100. Okay, that is what spectral reflectance is. And what is a curve then? What is a spectral reflectance curve? It is a graphical representation of the spectral response over different wavelengths of the electromagnetic spectrum, and it gives an insight into the spectral characteristics of different objects. Okay, it gives an insight into the spectral characteristics of different objects. And it is essential to interpret and analyze an image obtained in any one or more wavelength, that is one or two or three or multiple wavelength. Then only we will be properly able to characterize what the surface feature is. That's why we plot spectral reflectance curves. Means you need not plot every time. Once it is plotted and then you have to see. Now see this graph. This has been taken from a very important book in remote sensing and GIS, Lilly Sand. And this is a typical spectral reflectance curve for vegetation, soil, and water. Now you see here, this is reflectance in percentage. Okay, on y-axis, and this is wavelength. Okay, this is wavelength. First, we'll start with the dry soil, dry bare soil. That is gray brown. It is seen here in hatched lines, dotted in hatched line. You can see here this is for dry bare soil, and the reflectance is almost more or less similar at many points. You can see here it is almost increasing consistently, and then it has become constant. Okay, but in case of vegetation, it is more in 0.7 to up to around 1.3. So it is started increasing from this point, then increase, then constant, then it started decreasing again and decrease. So highest reflectance was between 0.6 to 1.2. And in case of clear water, it is just a very small reflectance, that too between 0.4 to 0.8. Okay, that too between 0.4 to 0.8. Okay, now what does this graph shows? This shows that for dry bare soil, we should have multiple wavelengths so that we can work out how work out the type of feature as well as the area. Plus vegetation green will have maximum reflectance between 0.7 to 1.3 and water between 0.4 to 0.8. Now I'll just read it and you have to understand. So average reflectance curves of healthy vegetation, dry barren soil and clear water bodies. This is for healthy features. And reflectance of individual features varies considerably above and below the average. Right. And the average curve demonstrates some fundamental point concerning spectral reflectance. There are some spectral reflectance point which shows us where it will vary in EMR spectrum. Now if you see one by one, we'll see now. This is for a healthy green vegetation. So spectral reflectance curve for healthy green vegetation exhibits the peak and valley configuration. Peak and valley means it will peak and then down, peak and then down. So peaks indicate strong reflection in the wavelength bands and valley indicate predominant absorption of the energy. That is absorbed. And you can see very well here that good absorption in visible region 0.4 to 0.7 micrometer. Okay, if you see here, this is reflectance, right? I already told you. But here it's absorption between 0.4 to 0.7 meter. And absorption reduces and reflection increases in the red infrared boundary near 0.7 meter. And after 0.7 is increased like anything, right? And reflectance and then is nearly constant to 0.7 to 1.7. It is constant line. And then as soon as the wavelength is increasing, reflectance is decreasing. So you have to keep in mind that between 0.4 to 0.7, absorption is more in visible region, and as long as the wavelength increases, the reflectance decreases. This is for a healthy green vegetation, 0.4 to 0.7. Now I would like to draw your attention to a very important concept, because this will be used for making a reference of other land use land cover features when you are doing it. Always keep in mind that infrared band, IR band. This I'm giving you a thumb rule based on my experience of working in remote sensing for last 10 years. And if you remember this, you will be it will be very easy for you to work ahead. Infrared band, IR band will have maximum absorption when there is chlorophyll available. Okay, that means if it is a lush green vegetation, if it is a lush green vegetation, chlorophyll will be more, because chlorophyll gives a green pigment to the plants. And if there is chlorophyll, the infrared waves will be almost fully absorbed, fully absorbed. That means if it is absorbed, the chlorophyll, the green pigment of the chlorophyll will look red in our other imageries, will look red in our other imageries. Okay, that thing you have to keep in mind. And with this reference, we can work out other things also. So you can see here that the spectral response of vegetation depends on the structure of the plant leaves. Here you can see the different things are there: upper cuticles, upper epidermis, okay, palisade cells containing chloroplast, spongy mesophyll cells, and lower epidermis. So here IR, infrared radiation penetrates the leaf as well as the mesophyll cell where it is reflected back. But when it is reflected back, it will be more of a more absorb as compared to reflection. The ratio will be less. That's why it will look red in infrared. Okay, it will look red in infrared, though it is green pigment. Okay, that is what you need to understand. Okay, that is what you need to understand as far as the vegetation is concerned. As far as the vegetation is concerned. Okay. Now, as compared to soil, you can see here that spectral reflectance curve for soil shows considerably less peak and valley variation. It is not as vary as this one compared to that of vegetation. The factors that influence soil reflectance act over less specific spectral band. There is no much specific band which you can account for. Okay, so there are other factors also which leads to this phenomena, like moisture content, soil texture. Right, soil texture, which includes proportion of sand, silt, and clay, surface roughness, and presence of iron oxide and organic matter. These factors are complex, variable, and integrated. Because of this, there is no single band, but then we have to make analysis based on multiple bands, and collectively we have to go for ground truth. And with the combination of all this, we have to work out whether it is a soil or not. Okay, because there are no peak and valley variation in that. Third one is, before that, one more thing what we need to understand is that if it is dry soil, its texture will be coarse, means reflectance will be less, and it will see dark in the satellite image, dark tone. But if the texture is fine, like sand or black cotton soil, reflectance will be more and the tone will be light, color tone. And also wet soil display reverse tendency. If the soil is wet, when it is dry, tendency is different. When it is wet, tendency is different. So moisture content reduces the reflectance, as you all know. So if it is a coarse texture, better drainage, less moisture content, good reflectance. Okay. If it is a fine texture, poor drainage, more moisture content, poor reflectance. Okay, means if the moisture is more, reflectance will be poor. If the moisture is less, reflectance will be high on the basis of wet soil and the drainage properties of the soil. Okay, if it is coarse soil, there will be more space for water to move in the system. And if it is fine soil, there will be less space for water to move. That's why fine texture, poor drainage, coarse texture, better drainage. Now we will see the spectral reflectance of water. Okay, here you see that it all is stored between 0.4 to 0.8. Okay, 0.4 to 0.8. So we need to understand something about the water only. Water provides a semi-transparent medium for the electromagnetic radiation. Okay, it is a semi-transparent medium. It's not fully transparent for the EMR because of the bed and something else. Okay, you cannot see even you leave alone EMR. Even if you would like to see, you may not be able to see fully penetrate into the water unless it is crystal clear. That's why we call it as semi-transparent. Okay, then electromagnetic radiations get reflected, transmitted or absorbed in water, and this spectral response varies with wavelength of the radiation, as I already mentioned, and physical and chemical characteristics of the water. Okay. Now, when water is in liquid phase, because we may not be encountering more ice anytime. So when the water is in liquid phase, high reflectance in the visible region between 0.4 micrometer and 0.6 micrometer and wavelength beyond 0.7 micrometer are completely absorbed. So if you wish to see the water bodies in an area, you have to have spectral bands between 0.4 micrometer and 0.6 micrometer. Then only you will be able to see. Otherwise, afterward, it will be completely absorbed. You will not be able to see anything. And if it is ice, of course, if it is a ice, that means it is solid and it will have all good reflections in all visible wavelength. You can very well see it is not liquid. Okay. So I hope spectral reflectance of these three rings are crystal clear to you. If you have any doubt by now, you can ask me. Otherwise, we will go ahead with the multispectral remote sensing. If you have any doubt, you can ask me. Okay. Multispectral remote sensing. So when I'm using this word uh, multi means there will be more than one spectra, right? So multiple sensors are used to sense the reflectance in different wavelength bands, and reflectance recorded in multiple bands are analyzed to find spectral reflectance variation with wavelength. And using the average spectral reflectance curves as the basic information, the spectral reflectance variation is used to identify the target feature. We will use more than one spectral radiance and then, spectral reflectance, and then we will collectively try to use all the bands and identify the target features. That's what we do in multispectral remote sensing. Now I'll give you one simple example. Just few slides before I was mentioning you about that why we need a infrared region, though we can see in visible region itself, right? I can see with the normal eyes also in visible region. Why I should go for infrared? That you will come to know now. Now here you see in this image, this is actual agricultural field which contains chlorophyll. This is trees. These are also trees. These are also trees which contains chlorophyll. But in this stadium, what greenery I am seeing, it is an artificial turf. It is an artificial turf. It is not actual grass. But with my naked eyes, I am seeing both. Okay. If suppose this right side figure is not there. So anyone will think that yes, this is also grass because it is green. This is also grass because it is green, but actually it is not so. But when I've seen it in IR region, infrared region, you see all the green pigments are seeing red. I told you already that because infrared will be absorbed, it will look red. But in the same case, when it was artificial turf, it is completely black because there is no chlorophyll in that. Right. That is the significance of working in different bands or multiple bands of a remote sensing. In one band, if you just go, okay, that I will see in the visible region, I will identify everything, it won't work like that. That's why you need, not you use, you need different spectral bands so that you can identify the target features. Okay, this I have already mentioned you. It is in normal color, is in IR. So artificial turf inside the stadium and the natural vegetation appears in the same color. And artificial turf appears dark, whereas the natural vegetation shows high reflectance in the IR region. Right? That you have to think in. Now, if you don't have any doubt, we will go for some important terminologies which we encounter, and then we will proceed with some other resolution related topics. By now, any doubt? No? In these two slides?
Sir, I have a doubt.
Yeah, go ahead.
Sir, although they are not, हर प्लांट में क्लोरोफिल नहीं होता, पर ऐसे प्लांट यूज करते हैं जिसमें एक क्लोरोफिल फिनोमेना नहीं होता, कुछ और होता है।
क्या तुम्हारा आवाज यार क्लियर नहीं, क्या पूछ रहे हो तुम?
Sir, I will write it. My voice
हाँ,
is
you're
not
right.
clear.
You're right. हाँ, you're right now itself. Meanwhile, anyone having good audio can ask any doubt. Or everything is clear to all. Yeah, so his question is, there are some plants which do not contain chlorophyll, some exception. How do yeah, actually when you work in remote sensing, those kind of things are negligible. Means it is not, it does not play a significant part in your overall objective of the project. So in those cases, you may leave also. One thing. Second thing, in remote sensing, we always report the data with 90 to 95% accuracy. So 5% of the time we ourselves admit that our interpretation may be wrong because of certain reasons. So that is the answer to your question. Because in 99% of the cases, the greenery will consist of chlorophyll. So if 1 or 2% cases, if there is not, that does not, it does not play a big role in overall analysis of our work. Okay, then we'll proceed if no other doubts. Okay, now we will see some important definition which we use in remote sensing system, especially related to satellites. Now, in this, we will understand what is meant by an orbit of satellite, what are the technical terms related to satellite orbits, and what are the types of satellite orbits. Okay. So first thing is that we have to understand what does a orbit means. So what is a satellite orbit? It is the path followed by a satellite in the space. Okay. Of course, it is a path followed by a satellite in the space. And it may be circular or near circular, or it may be elliptical also. Okay, it may follow complete circle. It may be near circular, it may be elliptical. It is not circular. Like this is circular. This is elliptical. In between there will be Earth. Okay, so this path followed by satellite in the space is called satellite orbit. And now we have to understand orbit based on some kind of definition which we require, which we use while selecting a satellite for different purposes. So first we need to understand orbital period, then altitude, apogee and perigee, inclination, nadir, zenith, and ground track, and swath. And these 6 definitions we will understand related to the characteristics of a satellite orbit. So first is the orbital period. Orbital period is what it is well understood that when the word period is used, it must be related to time. So time taken by a satellite to complete one revolution around the Earth. Okay, full complete revolution by the satellite and the time required in that is called orbital period. Okay, and it is spatial and temporal coverage of the imagery depends on the orbital period, and it varies from around 100 minutes to 24 hours. Okay, for some satellite it will be 100 minutes, for some it will be 24 hours. Okay, just for your information, spatial means
ചേട്ടാ ഞാൻ വിളിച്ചായിരുന്നല്ലോ, അത് TPMS ആണ്, ടയറിന്റെ പ്രഷർ അതിലല്ലേ സെൻസ്. എന്താ
Spatial means anything which is distributed in XY plane. Okay, XY plane. This is spatial. And if suppose this spatial image is of 1st January 112024. Okay, and same for same place I have a satellite imagery of 10th January also. So the time in between them is known as temporal, which is dependent on time, and whatever distributed in XY plane in horizontal plane is called spatial. So this spatial and temporal coverage also depends on the orbital period, and it varies from 100 minutes to 24 hours. Then comes altitude. So as you all know, altitude of a satellite is its height with respect to the surface immediately below it. So if this is the surface of the Earth and this is the satellite, whatever point below it immediately the surface of the Earth, the distance between them is known as altitude. So if it is a low altitude satellite, the altitude will be less than 2000 kilometer, and if it is a moderate altitude, it will be somewhere between 2000 to 36,000 kilometer. And if it is higher than 36,000 kilometer, it will be high altitude. That is called the altitude of the satellite sensor. Now comes the point apogee and perigee. So if this is Earth, let's say this is Earth and this is the orbit of the satellite. Orbit you know now very well. This is the orbit of the Earth. So apogee is what? Apogee is the point in the orbit where the satellite is at maximum distance from the Earth. Okay, because you know that every time it may not be in a single path. There will be certain times when it is far from the Earth, and there will be certain times when it is nearest to the Earth. So when it is far from Earth, it is called apogee, and when it is near to the Earth, it is called perigee. So apogee is point in the orbit where the satellite is at maximum distance from the Earth, and perigee point in the orbit where the satellite is nearest to the Earth. Okay, fourth one, inclination. As you can understand, inclination is the angle. So inclination of the orbit is measured clockwise from the equator. Okay, you know that if it is a Earth, equator is one which divides the Earth in two equal halves, right? It's an imaginary line which geologists use to understand things. So equator is something which divides the Earth in two halves, and it is a horizontal plane. Equator is a horizontal plane. With respect to that, there will be one orbit, right? Orbital track. So the angle between that horizontal plane and the orbital track I is known as inclination. Okay, so inclination of the orbit is measured clockwise from the equator. Okay, and inclination of remote sensing satellite is typically 99 degree. Okay, it is typically 99 degree. Now comes the point nadir, zenith, and ground track. So here you have to understand nadir. Now this is the point where radial line connecting the center of the Earth and the satellite intercept the surface of the Earth. Okay, radial line connecting the center of the Earth and the satellite intercept the surface of the Earth. In simple terms, it is the point of shortest distance from the satellite to the Earth surface. Okay, it is the point of shortest distance from the satellite to the Earth surface. And then what will be the zenith point? Any point just opposite to the nadir above the satellite will be zenith point. Okay, it is the zenith point. And what will be then ground track? You can understand very well from the word itself. The circle on the Earth surface described by the nadir point as the satellite revolves. And it is the projection of the satellite orbit on the ground surface. You can see in the next one. This one you can see now. This is the projection of the satellite on the surface of the Earth. Surface of the Earth. So if I go with this definition, nadir is the point of shortest distance from the satellite to the Earth surface. Okay, and zenith is what? Just above the satellite. Just above the satellite. So it will always move between the nadir and the zenith. And in between all those things will come altitude, then inclination angle and other things. Okay, and then come the swath width. Then comes the swath width. Now swath width is what? Swath of a satellite is the width of the area on the surface of the Earth which is imaged by the sensor during a single pass. Let's say this satellite is passing through the orbit and it has certain width which it will be capturing. So this width which it is capturing on the Earth is called the swath. Okay, it's called the swath. Okay, so I hope all the points are crystal clear to you. What's happening? Okay. Now we will understand about the types of satellite orbits. Types of satellite orbit. So there are three types of orbit: geosynchronous orbit, polar orbit, and sun synchronous orbit like IRS, Landsat, etc. One second. Huh? I think some construction will. Hmm. Okay, so up to this point, we just covered some kind of important definitions which may not be directly related to you, but it will be useful for you when you are working in remote sensing. And now we will just see the very important, very important concept which we require when you are dealing with remote sensing systems. Okay, and that is called as the resolutions. That is called as the resolution. Okay, now resolution means the power of sensor in terms of surface feature extraction. Okay, the resolution means the power of sensor in terms of surface feature extraction. It means the maximum extraction which it can do from the Earth's surface. It is called resolution. So first we will understand what resolution is, and then we will see types of resolution, and then we will also see which one is important for us. Okay. Now, first thing, what resolution means in remote sensing, resolution means the resolving power. Okay, and technically it is defined as the capability to identify the presence of two objects. Okay, capability to identify the presence of two objects. Also, capability to identify the properties of the two objects. Okay, an image that shows finer details is said to be finer resolution compared to the image that shows the coarser details. Now I'll give you an example. Suppose you have two binoculars with you, and if the resolving power is less, it will show two mountains or two stones, a single object. Though you can see the boundary, but it will seen in that particular binocular one object. But if you have finer resolution binocular, you can clearly see that that one image consists of two mountains. Okay, so resolution is what? It is the capability to identify the presence of two objects as well as their properties also, and it is defined by its resolving power. Now there are four types of resolution we read when we work in remote sensing. First is spatial resolution, second one is spectral resolution, third one is temporal resolution, and fourth one is radiometric resolution. Now I already explained you what does spatial means. Spatial means something which is distributed in XY plane. Okay, spectral I'll explain you, and temporal with respect to time. T for temporal, T for time. Okay, now we will slowly understand one by one all the things. Now you see this image. See this image. First we will understand spatial resolution. In this, what does spatial resolution means? It is the size of the smallest dimension on the Earth's surface over which an independent measurement can be made by the sensor. Okay, an independent one. An independent measurement can be made by the sensor, and it is expressed by the size of the pixel on the ground in meters. Okay, size of its pixel, and it is controlled by the instantaneous field of view, IFOV. We will understand this. So you can see here when it is coarse spatial resolution, objects are not very clear. But when it is fine spatial resolution, you can see even buildings also, their shadow also, and some shades also you can see. Okay, because it is a fine spatial resolution image. Okay, now we'll understand the IFOV. What does IFOV means? IFOV means the instantaneous field of view. Okay, it is known as the instantaneous field of view. Let's say this is a platform. This is a platform and there is one sensor. So anything, any camera or any sensor will have its own field where it can take the image. Okay, and when it is taking image, of course, it will be rectangular because we made it like that. Even if it is a circular earth, the image what we see will be in 2 dimension. So whatever rectangular it is forming on the surface of the earth, it is called as ground resolution cell. Okay, and it is also known as the instantaneous field of view. Now, if the altitude of this plane increases, let's say it is going up here, then this rectangular size will also increase, right? Because the more I go up, the more I'll be able to see. Just like you have taken one photo of a land from first floor of the building, and then you have taken photo of the same land from the 10th floor of the building. So the coverage area will be more. So with height, the coverage area will increase. But at the same time, with height, coverage area will increase, but resolution will decrease because you will not be able to see minute detail. But if you are taking the image from first floor, you will be able to capture minute details also. So it is what is called the instantaneous field of view. It is the angular cone of visibility of the sensor and area on the Earth surface that is seen at one particular moment of time. Though it is angular, but when it actually falls on the surface, it will become near to rectangular. Okay. And sometimes it is trapezoidal also. But since we are working in remote sensing, we will only always clip out our study area and then we'll work. And this IFOV depends on the altitude of the sensor above the ground level and viewing angle of the sensor. There are two things I already told you. It depends on the altitude as well as the viewing angle of the sensor. If that is the case, a narrow viewing angle produces a smaller IFOV and IFOV increases with altitude of the sensor. So here the instantaneous field of view will be small and here the instantaneous field of view will be high. Okay, then the ground resolution or the ground resolution cell. How we define it? The size of the area viewed by the sensor on the ground at one particular moment of time is known as pixel. Okay, it is known as pixel. And of course, it depends on the altitude of the sensor and IFOV of the sensor. And in remote sensing, it is referred as the spatial resolution of the remote sensing system. So whatever you have seen here, this rectangular ground cell, it is nothing but it is pixel. Okay, it is nothing but pixel. Now we'll understand slowly how finer resolution works. Let's say this is a house. Okay, this is a particular piece of land in which there is one house. Okay, and the size of that land is 30 meter by 30 meter. Okay, the size of the land is 30 meter by 30 meter. In that there is one house. So suppose my pixel size is 30 meter by 30 meter. My pixel size itself is 30 meter by 30 meter. In that case, since the house area is more, it dominates the area. The whole pixel will be classified as house because the resolution itself is 30 meter by 30 meter. It will not be able to bifurcate between the open area and the house area because resolution is 30 meter. Here you can see. So the signature from the house dominates for the cell, and as the entire cell is classified as house. Okay, that is first part. Second part, suppose I have increased my resolution and now I have a satellite image of 5 meter by 5 meter. Okay, 5 meter by 5 meter. So in that case, I'll be able to see this open area also. Right, but since this house is dominating these cells nearby, so the outer area where there is no house, there is open house, that will also be characterized into house only. Okay, but it is more accurate than the previous one So shape and spatial extent of the feature is better captured. However, some discrepancy is present along with the boundary. You can see a boundary also categorized into house. Only where the size was more than 5 meter, there only I am able to capture it. Now, suppose I have more finer resolution image. Now I have 1 meter by 1 meter. Okay, then I'll be able to identify even the boundary open area also, and I'll be able to properly extract the boundary of the house from satellite image because my resolution is more now. Okay, feature shape and extent is more precisely identified. Now, someone of you was asking about the radiation. That's what I mean to say that time. If the resolution is fine enough to counter that radiation, you can very well very well able to quantify radiation also. Otherwise, you may not. That's what I wanted to say that time. So I hope spatial resolution is clear to you. And if you see the classes of spatial resolution, there are 4 systems: low resolution systems, medium resolution systems, high resolution systems, very high resolution systems. So if it is more than 1 kilometer, it is called low resolution system. The examples of those satellites are MODIS and AVHRR that you have to read anyway. Second one is medium resolution system, in which spatial resolution is between 100 meter to 1 kilometer. Okay, for that the examples are Indian remote sensing satellite, Landsat thermal band, sorry, thematic mapper. TM is thematic mapper. Then MODIS, bands 1 to 7, all this. Then high resolution means the range is between 5 to 100 meter. Spatial resolution approximately in the range of 5 to 100 meter. Examples are Landsat ETM. ETM is Enhanced Thematic Mapper Plus, IRS List 3, IRS AWIFS, Spot, including panchromatic image, and very high resolution system, like when the resolution is less than 5 meter. Okay, what image will be giving you will be high resolution today, 30 meter, so that you will be able to work out properly. And the examples for these are GeoEye and Iconos and QuickBird. You can see, however, we don't require always very high resolution system. That is required for very specific intent, especially where there are some dispute or there is some defense related application. In most of the cases, 90% of the cases, high resolution system is enough. Very high resolution, we only go when there is certain conflict or some precise estimation of some important entities required. Now we'll understand the scale of an image, because when you are preparing a map, you have to put scale also on the map. So what does scale means? Scale is the ratio of distance on an image or map to actual ground distance. Okay. Maps or images with small map to ground ratios are referred to as a small scale, like 1:1 lakh. And those with larger ratios are called large scale, 1:5,000. Okay. Now what does it means? It means that when I'm saying that my scale is 1:1 lakh, it means that whatever is there on the map having length of 1 centimeter, on ground it will be having a length of 1 lakh centimeter, which is 1 kilometer. So 1 kilometer on ground equal to 1 centimeter on map. Okay, that was the scale of an image. Now, since you understand, so I hope up to this point it is clear to you. And now we will understand the spectral resolution of image. Spatial resolution, I hope clear to you. Now we'll go for the spectral resolution. Now, what does spectral resolution means? See, as the name indicates, it is resolution from spectrum side. It is not on the land. It is not on the basis of pixel, but it is on the basis of spectral. So simply speaking, no any technical part, the more number of spectrum you have available, more number of spectrum available, you have more spectral resolution. Simply to say, now you can see here, if you have only one band of between 0.4 to 0.7 micrometer, then you have single spectral image. If you have divided it in three parts, then you have three bands. So it is a three spectral image. If you are divided in five parts, then you six parts, sorry. So you have multispectral image. So this will having a highest spectral resolution. And why we do it, I told you already that when you are not able to identify certain things in a single band, you will try to work out the features, or you will try to extract the features using different bands available with you. So the more number of bands available with you, the more spectral resolution it is. So what does it means technically? Ability of a sensor to define fine wavelength intervals, ability of a sensor to resolve the energy received in a spectral bandwidth to characterize different constants of the surface of the earth. And the finer the spectral resolution, the narrower the wavelength range for a particular band. And the more they are, the more we will be able to work out from each band. Okay, that is called spectral resolution. And most of the remote sensing systems are multispectral using more than one spectral band. Of course, we use more. Like IRIS list, it uses 4 bands: green, red, near infrared, and mid infrared. And this Equatorial Modis instrument use 36 spectral bands, including the visible spectrum. So you can imagine the amount of information which we can extract from all these things. And now there is a concept of hyperspectral sensor also, which detect hundreds of very narrow spectral bands in between these bands itself. Okay, so this is what is called spectral resolution. So I hope spatial and spectral resolution both are clear to you. And this I have already told you that different features are identified from the image by comparing the responses over different distinct bands, and broad classes such as water and vegetation can be easily separated using very broad wavelength ranges. Okay, like visible and near infrared. And for more specific classes, we have to see like type of vegetation, rock classification, much finer wavelength will be required. Like I'll give you a simple example, and anyway, second half you will be seeing how we will do the satellite data analysis. But you should understand this basics what I am showing you now, so that you will be able to understand. But I'll give you one example here. Here, actually, these are agricultural fields. How I can say is that there are well-maintained patterns, right? There are well-maintained patterns. So I can very well say that it is an agricultural field or some kind of an anthropogenic activity. But these are coarse and unstructured form, these trees and all. Somewhere it is there, somewhere it is not there. So even though it is a vegetation, even though it is vegetation, in that also, if I have more spectral bands, in that also I'll be able to make more classification, that which will be man-made and which will be anthropogenic. Sorry, anthropogenic and man-made are same, which will be man-made and which will be natural. This thing I'll be able to work out. That's why the spectral resolution plays a big role in remote sensing. Okay. Now we will see third one, which is called as the radiometric resolution of the image. Okay. Now you have to understand this in a different way. First one was based on the size of the pixel on the land. Okay. First one, the spatial resolution was based on the size of the pixel on the land. Second one was in that pixel, how many different wavelength bands are there available with me to work upon. Okay. The third one, radiometric resolution, is basically in a single color or in a single gray image, how many shades of that gray or black I can obtain. Okay. Land, spatial resolution, spectral wavelengths, spectral resolution. In that color, how many different shades I can obtain? It is called as radiometric resolution. Now I will explain you this in briefly. Radiometric resolution, it is what? Sensitivity of the sensor to the magnitude of electromagnetic energy. And how we do it is that how many gray levels are measured between pure black, no reflectance, to pure white, maximum reflectance. Okay, the finer the radiometric resolution of a sensor, the more sensitive it is in detecting small differences in the energy. Okay, the finer the radiometric resolution sensor, the system can measure more number of gray levels. That is what I was saying. Okay, then Just 1 minute. This is for solar panel. Here, huh? And this radiometric resolution is measured in bits, and each bit records an exponent of power of 2. And maximum number of brightness levels available depends on the number of bits used in representing the recorded energy. Now, I know this will be a little bit difficult for you to understand, but I will understand this with an example. Suppose your radiometric resolution is 1 bit. So number of levels of gray will be 2 only, which we can say that black and white, only black and white. But if it is a 7-bit image, the number of levels of that color will be 2 raised to the power 7, means 128 level. So between gray and white also there will be 128 shades of gray, then slowly turning to white. Okay, if it is 8-bit, there will be 256 levels of radiometric resolution in that. Means you will have 256 shades of one color in the image. And if it, of course, if it is high resolution 11-bit, there will be 2048 levels of color in that. Okay, now we'll understand like this. Suppose this is a pure black color and this is a pure white. In between there are 3 shades. Black, then if I lighten it, it will be dark gray. If I more lighten it, mid gray, pale gray, and ultimately it will become white. Okay, now we'll understand the radiometric resolution. So suppose if it is black, its digital number will be 0, there will be no reflectance. For white, digital number is the maximum 1. Okay, so if it is 1 bit, there will be two colors only, 0 and 1, black and white. If it is 2-bit, there will be 2 more included. If it is 8-bit, 255 more shades in between, like this it will come 1, 2, 3, 4, 5, 6, 7. That much you can see. And if it is 10-bit, 1023 colors you can see in between. Okay, so radiometric resolution is what? It is on the basis of the color of the satellite image, and mostly it will be between black and white. Based on this also, we can work out so many things. Okay, that you will see slowly once you start working in the area. Here you can see one example. See, it is a 2-bit data. Okay, and this is 8-bit data. Now you yourself see image is same, but since it is only 2-bit data, the more colors are of gray and white, then slightly gray and then white. But I may not be able to properly work out something from it. Here also I'm seeing white. But when the resolution is fine, it is 8-bit, 256 different shades of gray are there. 256 different shades of gray and white are there. So there I can very well see some or the other objects that yes, it may be different. That's why when the final radiometric resolution is there, it increases the data storage requirement, but at the same time, it will give you the precise estimation of things. Okay, and I hope you understand now. The finer the radiometric resolution, the more number of gray levels you can achieve, and more details can be captured in the image, which is what our objective is. Okay. Now temporal resolution. This is the last one, and we will understand what temporal resolution is. I already told you T for temporal, T for time. So number of objects an object is sampled, or how often data are obtained for the same area. And it is also called as the repeat cycle of satellite. So the absolute temporal resolution of a remote sensing system to image the same area at the same viewing angle a second time is equal to the repeat cycle of satellite system. And the repeat cycle of near polar orbiting satellite is usually several days, like 24 days for IRIS-1C, 18 days for Landsat, and 14 days for ICONOS. Like that is goes. And the actual temporal resolution or revisit period, we can also call it as a revisit period, where on the same place it will be coming in of a sensor, depends upon the satellite sensor capabilities and swath overlap and latitude of that area. So temporal resolution is nothing but in 1 year, how many times it has crossed the same place for capturing the image. Suppose in 365 days, it has crossed 36 times. So 365 by 36, 10. Every 10 days, it has passed 1 time. Like that, we can find the temporal resolution. Now, before I go ahead, I would like to hear from you. Is there any doubt till now, specifically in these resolutions, since it is an important concept? Anything? So you all understand everything. Mega Pradeep, are you there? You able to hear me?
Yes, sir.
Okay, so can you just briefly describe what is spatial resolution?
Spatial resolution can be of it can be of size. We can determine the size of the smallest dimension on Earth's surface, and it is independent of the measurement made by the sensor, and it can be expressed by the size of the pixel in ground by meters, and it can be controlled by the IFOV.
Okay. Okay. Raj Kishore Dalai on hold. Rahul Chilawar. Rahul Chilawar, you there? Upasana Singh, are you there?
Yes, sir.
Okay. Can you just briefly describe what is IFOV? Upasana?
Yes, sir.
Yeah. Can you describe what is IFOV? Instantaneous field of view.
Sir, it is a cone of visibility of corner uh, and depend on altitude of sensor and viewing of angle of sensor.
Okay. Okay. Good. Vivek Tandon, are you there? Vivek? Okay. Zulfikar Ahmed? जुल्फिकार अहमद सुन पा रहे हो मुझे? हाँ, तुमने माइक तो अनम्यूट किया है पर आवाज नहीं आ रही तुम्हारी। जुल्फिकार, प्रार्थना, you able to hear me?
Yes, sir.
अच्छा, प्रार्थना, can you just brief what is spectral resolution?
Sir, in spectral resolution, uh, so we do Uh, I understood, but I am
Oh.
unable to
Okay. Okay, no issue, no issue.
answer.
Okay, no
Sir,
issue. Yeah, tell me. Go ahead.
so we through sensors. So sorry, I'm unable to recall an answer.
Okay, so we'll proceed further. Anyway, we have almost come to the end of our talk. Not much things are there now. Okay, so last one, temporal resolution. What is the importance of it? So actually, when you have images of different time periods, it is very important to understand that when you have images of different time periods, it will be very useful for you to work out the changes in that land and also to plan for the future. So images at different time periods show the variation in spectral characteristics of different features over time, and its application include land use land cover, classification temporal variation in land use land cover, as well as monitoring of a dynamic events like cyclone, flood, volcano, and earthquake. So this temporal resolution plays a big role. Then only you will be able to identify the change. Okay. Then only you will be able to identify the change in a certain study area. Okay. Now here you can see here that there was particular non-flood year. Okay, in 1988, and there was flood year in 1993. So because I have temporal images, I can very well see that earlier water was flowing from here, and now because of flooding, this much area is submerged. So that I can now frame some policies, or I can make some mitigation measures for before the next flood occurs. That is how temporal images are useful. And also a temporal variation in the spectral signature can be estimated. We can very well see in different spectral, and it is also useful for seeing the presence of features over time. And continuous change in the vegetation characteristics can be monitored. Okay. And as I said earlier, it is used to classify crop types, whether it is perennial or long or short duration crops. Some crops will be there which are parallel all along the time, and some will be for certain duration only. So to identify those type of crops, temporal variation is also important. Now I will just give a brief of some of the remote sensing system features. What all types of satellites are there and what are their features. There is no much technical in that because I have already explained to you. And but I want you to be aware of what all satellites are available to work on. So we have remote sensing satellite programs of India itself, then Landsat program by USA, Spot mission, our very own IRS satellite program, and then there are very high resolution satellites like Iconos, QuickBird, and geostationary satellites. So if we start with the Landsat program, it is the longest running program by now. And first time it was launched in 1972. One case study I'll be showing you the fourth day, that is day after tomorrow. There you will see that how we have taken one satellite image of 1972 and how it is work. Okay. And earlier it was known as Earth Resource Technology Satellites, and now it is named as Landsat. So this is the timeline of different satellite. Landsat 1 1972, Landsat 2 1975, 1978, and so on. And in that there are certain sensors used like return beam Vidicom RBV, multispectral scanner, thematic mapper, enhanced thematic mapper, and enhanced thematic mapper plus. So these three only are in use now, from thematic mapper to enhanced thematic mapper plus ETM plus. And all these satellites are sun synchronous near polar orbit satellites. Okay, all these satellites. And this is their characteristics. Now I hope you know all these things. Orbit you know, altitude you know, inclination you know, right? Number of orbits per day you know, swath width you know, spatial resolution you very well know, radiometric resolution you very well know. So the purpose of showing you all this definition was that so that you can read a satellite, you can understand a satellite whether it is good for you or not. So and these are the various characteristics of different Landsat program. This is Landsat 1, 2, 3 and Landsat 8. So these details I will not go through it. These are just numerical values which you should remember only. Okay, and as I said earlier, Landsat satellite typically completes 14 orbits in one day. Then as far as spectral sensitivity is concerned, I showed you 5 sensors: return beam, a BDCOM, multispectral scanner, thematic mapper, enhanced thematic mapper, and enhanced thematic mapper plus. So RBV has 5 bands, MSS is also 5 in different wavelength, and thematic mapper is more numbers. You can see 1 to 7. Okay, and ETM has more, B1 to B7. These are also there, plus one additional is also there, and these are same as ETM. So you can see now 8 to 9 bands are there for us to work upon. Okay, and you can see here that which spectral band can be used for what kind of detection. Like this band can be used for coastal aerosol detection. This is a blue band, this is a green band, this is a red. 0.85 to 0.8 is near infrared. These two are short wave. This is panchromatic, this is cirrus cloud detection, and these two are thermal infrared. This case study also I'll be showing you how we have determined the land surface temperature of Nagpur city using thermal band. Okay, then there was one spot system which was by European country France, and it is called as spot, which is some abbreviation in French language. And this was the first satellite of the mission Spot 1, and it was launched in 1986. And first are the observation satellite that used the linear array of sensor and the push broom scanning technique. Actually, these are not even in our scope also. This is purely related to space science. But this was a kind of innovation in satellite program that you can understand in that way. And also these various timelines of the Spot mission is also given when it's started all. Then also there are 5 programs by now: Spot 1, 2, 3, Spot 4, and Spot 5. So like previous one, with each mission passing by, it is improving. With each mission passing by, it is improving. Okay, these are also again the spectral details of various Spot missions. This is for Spot 4, Spot 5. This is for Spot 6. And again, based on that parameter, what I showed you: orbit, altitude, inclination, sensor, bands, spatial resolution, radial resolution, these characteristics are given. Okay. Then our very own, our Indian remote sensing satellite system, where the first satellite was launched in 1988. It was called as IRS-1A, Indian Remote Sensing 1A. And that was also sun synchronous near polar orbit, low altitude satellite. And by now there are 4 sensors in that: LIS-1, LIS-2, LIS-3, PIPS, and AVIVs. Okay, and they are majorly using it for agriculture, hydrology, geology, drought and flood monitoring, marine studies, and land use analysis. So LIS-1 and 2 has 4 bands. LIS-3 also has 4. LIS-4, 3. PIPS has 2. But this all can be used in combination with each other. Okay. And similarly, on the same parameters: orbit, altitude, inclination, sensor, bands, and spatial resolution, radiometric resolution, these satellite sensors are also categorized. Okay, and this is just a demo of IRS P6 Resource Set 2 satellite, which is a multispectral mode image, shows a particular area in France in natural color. So you can see the clearness of Resource Set 2, IRS P6 Resource Set 2. And on last day, we will be giving you one lecture on how you can download these satellite images and what are other resources which you can use from remote sensing perspective. Okay, there are some more images of Himalayas and the same city. And one more satellite is launched. It's called Iconos. It's a high resolution image and it is commercial. I told you that in some cases, when the precise estimation of land feature is required, we use Iconos. Okay, when the spatial resolution can be up to 0.5 to 0.1 meters. Okay, this is Iconos image. You can see here that it is 0.8 meter. So you can see that in the desert area in Saudi Arabia, they are able to quantify even the diameter and the proper area also of that agricultural fields. This is 0.8 meter resolution only. So you can understand up to 80 centimeter object can be very well classified and captured in the satellite image. Okay, and then this is the across image of the Denver Broncos Stadium, Denver, Colorado, USA. And also you can see that even the different shades in that stadium you are able to see. Okay, and as I told you earlier, it is a very high resolution satellite image. And one more is there called QuickBird, and it can go up to 0.61 meter to 2.4 meter. Even that means a 0.61 meter means 60 centimeter of object can also be very well extracted using these high resolution systems. And this is the same classification based on orbit, altitude, inclination, spatial resolution, and radiometric resolution for that satellite. So by now you would have observed that for each satellite, I am giving you the required parameters also. So when the recording has been uploaded on YouTube, you can see it readily. And this is also a QuickBird image. This is a true color image having a spatial resolution of 61 centimeter. So you just see even the smaller trees girth is also you are able to see. Means the size of this dot, what I am using as a cursor, the size of the dot of the tree also you are able to see. You can see here individual trees also. So you can very well just take the image, you can count the trees in the area and you can report to a authority without going to the site. This is the power of remote sensing. Okay. And there is one also inside program where our IRS has extended their services for inside program. Those are called Indian National Satellite Systems. And this is also one of the largest domestic communication system in the Asia Pacific region. These are all geostationary satellites orbiting at around 36,000 kilometer altitude. Okay. And initially it was started in 1983. And there is one more called GSAT, Gagan coverage, and this is the recent one in instant program. But afterwards, one more is there. One more is there that I am not shared here, but it started giving its services in 2012. But this satellite is not for satellite image purpose. This is for communication and navigation purposes. Okay, this is only for communication and navigation purposes for ships, for government vehicles, for defense army, all those kind of vehicles. And there was one more called Kalpana 1. It was named after our Indian born astronaut Kalpana Chawla. So it was launched in September 2002. And this was originally named as MedSat, but it was renamed as Kalpana because of the said demise of Kalpana Chawla in her memory. Okay, and this was also launched by ISRO only. So this is also a different kind of sensor which gives other add-on values to whatever satellites I have presented you by now. So with this, our today's session is over. I hope all the basics and all were crystal clear to you. So these recordings I'll immediately upload. I'll try to upload immediately. And the second half, when Anish Kumar R will be taking the class, these basics will be useful for you. So if you have any doubt, you can ask me. Otherwise, we will break for lunch. Now it is around 12:25.